Introduction to Algorithm Design. We'll cover the control structures which form the basic building blocks of all algorithms, which are sequences, selection, repetition, and subroutines. Sequencing is the specific order in which instructions are performed in an algorithm. It is a structure to make sure that the steps in an algorithm are performed in the right order, otherwise the algorithm will not work correctly. In a selection structure, a question is asked, and depending on the answer, the program takes one of two courses of action. By having selection, you are able to have more routes and choices in your algorithm.
Repetition structures, or loops, are used when a program needs to repeatedly process one or more instructions until some condition is met. This can be seen in the flowchart, where the algorithm keeps repeating until the condition is false. Subroutines, better known as functions, is a block of organized, reusable code that is used to perform a single, related action. Functions, in their basic understanding, combine many instructions into a single line of code.
Pseudocode is a preliminary form of code instead of humans and not computers, intended for humans, not computers. It is used as a formative method to allow you to put your thoughts on what you would like to code on paper. Pseudocode has some conventions while making them. For example, all structure elements must come in pairs, such as a beginning or an end. All keywords are in capital, and indentation is used to show structuring and nesting. We can see from this example that the if and while come in pairs are in uppercase. There is also indentation to show structure. Some ways of showing how sequences run include the binary selection, which allows the selection of two possible paths depending on the condition. The multi-way selection allows for any number of possible choices. Repetition allows for a portion of an algorithm to be done as many times as needed.
Flowcharts. Flowcharts, just like pseudocode, are representations of how algorithms work. They also follow conventions. They visually show how algorithms work. So for the terminators, start and end, they are in ovals. For inputs, they're parallelograms. For decisions, they are diamonds. For processes, they're rectangles. One thing not shown in this diagram is arrows. All flowcharts require arrows to show the direction of the code. The one type of flowchart is a binary decision flowchart. For this, you can have one result end in a process and the other result just continue the code, or each result ending in a process. There are also two types of loops, pre-test loops and post-test loops. Pre-test loop, like this one, tests the condition before it carries out the process. And it carries out the process over and over again until the condition is false. Post-test loops carry out the process no matter what the initial time, and if the condition is false, then it continues to carry out the process until it becomes true. This is a multiple decision flowchart. For this, you can add as many processes as you want, and also as many choices as you want. And they also have to have an otherwise option because the user might choose another option. Oh yeah, this is an example of code that was used for R1. So this was a timer where we created a time variable, and then while it was greater than 0, we waited 1 second and then subtracted 1 from the timer. So that's the flowchart version of it and the pseudocode version of it. For our movement algorithm saw the pseudocode version and the flowchart version.
Each algorithms must use appropriate values to ensure that the logic within the algorithm is understood by the viewers. This is crucially important for developers to implement these routines into their code because it helps them understand the processes that occurred once they see the end result. Elements in an array are mainly indexed in zeros or ones. Loading an array and printing its contents. An array can be loaded from data values or input hardware, such as keyboards. Algorithms declare that the values are read from a list of data statements until a sentinel value of XXX is shown. As you can see in this example, it shows that the sentinel value is not to be loaded into the array. The pre-test loop is to ensure that if no data is present in the list, then the loop will never be loaded. The second example is an algorithm that prints an array. To print an array, there must be a variable that stores a number of elements in the array. However, if the number of elements are not recognized, the sentinel value would be stored into the last element in the array, and the printing will proceed until the value of XXX is made. Adding the contents of an array of numbers. To add contents of an array of numbers, there must be a counter that reveals the number of elements in the array. On this example here, if a number of array of elements are unknown, the sentinel value would be stored into the last elements in the array, whilst the total continues to stockpile until the sentinel value is met. On the second example, it has a sentinel value of 999. The pretest loop on this example ensures that the sentinel value 999 is not included in the total.
Advantages of algorithm development. They require a structured approach which goes step by step. It explains visually how you go from beginning to end. Here is an example of an algorithm which explains part of a game. So we start off at the top and move all the way down to the bottom. Here is an example of an algorithm that we developed for the Term 1 Yahtzee program. Here we can see that we begin the full house operation and move all the way down to resetting the roll counter. It checks by showing the diamond box, it shows the operation that is being conducted and two ways that it goes. False. If it's false, it adds the full house total to 0 and then moves down to disable the full house button. It provides an easy flow and allows easier interpretation for various people. And it is easy to develop by us drawing by hand and also using computerized drawings.